This video, we will discuss about critical resolved shear stress. So before we move to critical resolved shear stress, there's a big name. So let us look at what kind of, we were discussing about the slip. That means what kind of stress is required for slip? What kind of stress is required for slip? That means you have seen uh, slip occurring. That means one part of the crystal structure slides over another, right? That is what happens in crystal. There is a happens in a slip. So this is what happens in slip. See, for this occur, you need a shear stress. Okay, so a shear stress is required. That is essential. A shear stress is required on the slip plane. Okay, on the slip plane in the slip direction. Okay, in the slip plane in the slip direction. But you know that the plastic deformation, okay, that is the slip, the plastic deformation occurs, mm, also happens in uniaxial tension. Okay, that means when you are, uh, see, earlier when we done a uniaxial tensile stress, that means when a material was loaded like this. So that was a uniaxial tension. In that case also, you had a plastic deformation, a cup and cone like shape was formed. Okay, so cup and cone shape. So during fracture, it occurred like that. So that means a plastic deformation occurred. That means there was slip. So we have seen that plastic deformation occurs also in uniaxial tension. Okay, now our question is, do shear stress develop develop due to an applied due to an applied tensile stress due to an applied tensile stress? Okay, so if shear stress is developed, then the problem is, the answer is yes. The answer is yes, a resounding yes. Shear stresses, okay, so shear stresses on a slip plane on a slip plane in a slip direction in a slip direction due to an due to an applied tensile stress due to an applied tensile stress is called the resolved shear stress is called the resolved shear stress is called the resolved shear stress. Okay, now let us find out the resolved shear stress due to an applied tensile stress. Okay, that is resolved shear stress due to an applied tensile stress. So let us take a specimen, a body like this. So it has got a cross section here. It has got a cross section, right? So you are basically loading it. You are applying sigma here. Okay, then so we will take an inclined plane here. Okay, so this is an inclined plane. Okay, and this is the vertical axis. And this line is perpendicular to this plane. So this angle is phi d, and this angle is phi n. So let me redraw it. So make it a little more clearer. So this one. Okay. So now it is much more clearer. It is phi n and phi d. So these are the angles. So this plane, that is an inclined plane. So uh, the normal to that inclined plane with this vertical axis will give you phi n, and you have the angle phi d also. So here the sigma is the applied tensile stress, applied tensile stress, and n is the slip plane normal. So see, this one is n. Okay, slip plane normal. Okay, so the inclined plane is our slip plane, and d is the slip direction. So this is d. So this is the slip direction. Okay, and phi n is the angle between, okay, angle between the tensile axis and slip plane or plane normal. And this phi d is the angle between tensile axis, tensile axis and slip direction. This A is the cross-sectional area. This cross-sectional area. AS is the area of slip plane. Okay, this is area of the slip plane. Okay, the area of slip planes means that inclined plane. So, what is tau RSS? That is resolved shear stress on the. You need to find the resolved shear stress on the slip plane. Okay, on the slip plane in slip direction. In slip direction. So first let us find the area of the slip plane in terms of the normal area. So that is given by A by cos phi n. So let us look this figure. So this is the inclined plane. You can see that this inclined plane is like this. Okay, and this is the angle, right? So if I draw here, this is the inclined angle, and so this angle is phi d. Okay, and this angle is phi n. Okay, and this area is the A. Okay, so that means this inclined plane will be definitely greater than this. AS will be definitely greater than A. When it is inclined, you can see that this AS, so what will be this angle? This angle is phi n. Okay, so I will just draw the lines only. So that means you need to find this one. So this is your angle. So this is A and this is AS. Something like that. Okay. So this angle comes out to be phi n. Okay. So AS is equal to A by cos phi n. So force acting on A is force acting F is equal to sigma A. So that is component of F in direction D is given by FD. If you resolve the force, you can see that you have sigma in this direction. So force in this direction, you can write it as F cos phi d. Okay, that is F cos phi d. So resolved shear stress tau RSS is equal to this force divided by the uh, area of the slip plane. This is equal to F cos uh, phi d divided by A by cos phi n. Okay, this is equal to F by A cos phi d cos phi n. Okay, so that is F by A is given by sigma cos phi d cos phi n. Right. So that is the resolved shear stress. Okay, and this is the resolved shear stress. So let us draw some special configurations here. Okay. So consider a planes like this. That means a plane that is normal. Okay. So that means here you can see that here, so you have a normal plane. So here you can see that phi d is equal to 90 degree. And you have another configuration here in which I am considering a plane like this. So here the planes are like this. Right? So this is vertical. So in this case, the phi n is 90 degree. Okay. So in both cases, if you look at the formula, this tau RSS is equal to sigma cos phi d cos phi n. So if phi d is 90 degree and phi if either of them is 90 degree, that means this will be 0. So resolved shear stress in both these cases are 0. If you take a plane like this, that is perpendicular or parallel to the main area, so that will be resolved shear stress will be 0.